One evening soon, your city will go dark. Not just a flicker, not just the lights in your living room, but a wide, sudden blackout that takes down apartment blocks, elevators, traffic lights, and the quiet data centers humming at the edge of town. Your phone screen will still glow for a while, but the apps you live in will start failing one by one. No food delivery. No streaming. No cloud. You will feel something you rarely notice anymore. The raw, physical dependence your entire life has on invisible rivers of electricity. Now imagine that, while you are staring at that dead skyline, someone tells you this. A few years earlier, in late 2022, a group of scientists in California briefly lit a miniature star on Earth and proved that your world does not have to run the way it does now. That sentence sounds like science fiction, but it already happened. And the strange part is how quietly it slid past your timeline. You scroll past arguments about power bills and climate targets. You see headlines about heat waves and failing grids. In the middle of all that, a laser shot at the National Ignition Facility at Lawrence Livermore National Laboratory crossed a line that scientists had been chasing for decades. To see why that moment matters to you, you have to rewind the story of your own electricity. Right now, most of the power touching your life comes from burning something. Coal crushed and fed into furnaces. Gas forced through turbines. Oil refined into fuels that move ships and planes and backup generators. Even in countries that are rapidly adding solar panels and wind farms, fossil fuels still lurk in the background, filling gaps, feeding peaks, keeping servers online at 3 in the morning when the wind dies. Every time you turn on an air conditioner or fire up a video call, you are leaning on that system. And it is cooking the sky you live under. Fusion is the opposite kind of fire. Instead of tearing big molecules apart, it gently forces tiny atomic nuclei together. In the core of the sun, gravity squeezes hydrogen so brutally that those nuclei fuse into helium, and in the process, they release an enormous amount of energy. No smoke. No long-lived radioactive waste. Just light and heat pouring outward for billions of years. On Earth, gravity is far too weak to copy that directly. So if you want to make a miniature star here, you have to cheat with technology. You either trap a hot, charged gas with magnetic fields and swirl it in giant donut-shaped machines called tokamaks and stellarators. Or you hammer a tiny pellet of fuel from all sides, with lasers so intense that inertia itself holds the implosion together for a heartbeat. In both cases, you are trying to do something that sounds simple and turns out to be brutally hard. Get more energy out of fusion reactions than you put in to start them. That goal has a name: ignition. It is the difference between lighting a match and watching it fizzle, and lighting a match that starts a bonfire. For most of the 20th century and the early 21st, ignition lived in presentations and equations, not in hardware. Machines got bigger and more complex. Shots came closer and closer. But something always leaked away: heat, confinement, symmetry. People who worked in fusion labs joked, a little bitterly, that commercial fusion was always 30 years in the future. While you were getting your first smartphone, teams at Lawrence Livermore were quietly building the most powerful laser system on the planet. While you were learning to live inside social feeds and video calls, engineers and technicians were learning how to polish microscopic fuel capsules more smoothly than a mirror and align 192 beams of ultraviolet light down to a fraction of a millimeter. One of the key people in that effort is physicist Omar Hurricane, the chief scientist for the Inertial Confinement Fusion Program at the National Ignition Facility. Another is experimental physicist Kritcher, who led the design of many of the crucial laser shots in the early 2020s. Alongside them, plasma physicist Tammy Ma worked on the experiments and the broader strategy for crossing the ignition threshold. Their days did not look like movie montages. They looked like code and calibration and endless meetings about why a simulation did not match a detector readout. They were learning how to choreograph violence at microscopic scales. On that December morning in 2022, the outside of the National Ignition Facility looked boringly normal. Low buildings, parking lots, security gates. Inside, at the center of a concrete sphere the size of a small house, a frozen bead of deuterium and tritium fuel sat inside a tiny gold cylinder called a hohlraum. It was no bigger than the eraser on a pencil. Around it, those 192 laser beams waited in long tunnels filled with carefully aligned optics. When the shot began, the lasers did not point directly at the fuel. They poured their energy into the inner walls of the gold cylinder. The cylinder flashed into a bath of X-rays that wrapped the fuel in light from all directions at once. The outer layer of the fuel pellet blew off under that blast, and the reaction slammed the rest of the shell inward, crushing it toward its own center. In that collapsing moment, the density and temperature in the core of the fuel approached those in the heart of a star. Normally, the positively charged nuclei inside hydrogen strongly repel each other. They are like tiny magnets flipped the wrong way around. But when you squeeze them hard enough and heat them high enough, that barrier breaks down. Nuclei start to fuse. They release energy as fast neutrons and alpha particles. In the shot that finally worked, those alpha particles did something crucial. They did not escape. They stayed trapped long enough to dump their energy back into the fuel, heating it further from the inside and causing even more fusion. For a few trillionths of a second, the reaction fed itself. From the perspective of the tiny fuel capsule, the experiment crossed the line into ignition. The detectors at NIF saw more energy come out in the resulting fusion than the lasers had delivered to the target. That does not mean a power plant was born that day. The entire facility still had to draw far more energy from the grid to charge the lasers than it got back from the shot. But in physics terms, the bonfire finally lit. You live in the psychological shadow of that moment, whether or not you remember the headline. For the first time, scientists could say, in a lab on Earth, that they had created a tiny volume of star-like plasma that was self-sustaining for an instant. Now come back to your life at the 4 or 5 minute mark of this story. This is where your attention usually slips. You have heard about lasers and fuel pellets and strange acronyms. Your brain starts to drift toward notifications and everyday worries. So here is the twist. The real drama of that miniature star is not inside the lab at all. It is inside your future. Picture 2 different versions of your city a few decades from now. In the first version, nothing fundamental changes. Your demand for electricity keeps climbing as artificial intelligence, crypto, streaming, electric vehicles, and automated factories all chew through more and more power. The grid strains. To keep up, governments and companies dig up more fossil fuels, build more gas plants, and tell you that efficiency and offsets will be enough. Heat waves get worse. Blackouts become more frequent. Your weather app becomes less about small talk and more about survival planning. In the second version of that city, something underneath the skyline has changed. Out on the industrial edge, there is a boxy building you rarely think about. Inside, powerful magnets or advanced laser systems run on cycles you never see, confining or compressing fusion fuel over and over. Instead of fuel trains and tankers, that plant receives small shipments of hydrogen isotopes. Instead of smokestacks, it has thick shielding. Its main product is a steady flood of clean electricity, feeding into the same wires your life already hangs on. In this version of your city, the data centers that host your memories and work are fed by a fire that does not darken the sky. Your worry shifts from, do we have enough power without wrecking the climate, to, how do we use this better? Ignition in 2022 does not guarantee that second city. But it makes it real enough that engineers, investors, and policymakers have to treat it as more than a fantasy. After that shot, research programs around the world recalibrated. Magnetic fusion projects, like the ITER tokamak being built in southern France and the SBARC reactor planned by Commonwealth Fusion Systems near Boston, could point to NIF and say, the core physics works if you get the conditions right. Fusion startups suddenly had a fresh story to tell about timelines. Governments had a concrete milestone to justify sustained funding. Even in other fields, the ripple was felt. At places like the DIIID tokamak in San Diego, researchers published results on how the high-energy particles produced in fusion reactions might actually help calm the turbulent eddies of plasma that normally sap energy from the core. The closer your species looks, the more fusion begins to look like a difficult engineering problem instead of an impossible dream. And you are very good, as a species and as an individual, at turning difficult engineering problems into pocket-sized miracles. Think of the first time you streamed high-definition video on a phone. Decades of fiber optics research, semiconductor physics, and wireless engineering were compressed into a gesture so simple that a child can do it. From the outside, it looked like magic. From the inside, it was the slow accumulation of 10,000 small improvements that built on a few big breakthroughs. The miniature star in that whole realm is one of those big breakthroughs. It is not the end of the story. It is the place where the story stops being hypothetical. There is a gap between ignition in a single, carefully tuned shot and a power plant that runs safely and profitably for years. Lasers have to become more efficient and much faster, firing many times a second without destroying themselves. Fuel targets have to be manufactured by the millions, at low cost, and delivered in precise streams. Materials have to be invented that can survive constant bombardment by neutrons without cracking or becoming dangerously activated. Control systems have to handle wildly complex plasma behaviors in real time. Magnetic designs have to tame disruptions, those violent collapses of confined plasma that can damage reactor walls. None of this will be easy, but none of it requires the laws of physics to change. It requires something you already know how to do: iterate. People like Omar Hurricane, Kritcher, Tammy Ma, and thousands of unnamed colleagues have shown what that looks like. They did not get ignition by building a perfect machine on the first try. They got there by being patient, by staring at error bars, by reshaping laser pulse profiles, by rewriting code, by questioning their own assumptions over and over. They treated a star not as a miracle, but as a problem in symmetry and timing. Your own life is full of small versions of that attitude. Every time you update software, refine a workflow, or learn from a mistake in your own projects, you are practicing the same kind of incremental stubbornness. The difference is scale. Their experiment changed what is possible for the way your entire civilization might power itself. So when you hear the phrase, a fusion shot that made a miniature star on Earth for a moment, you can decode it now. It is not a metaphor. It was a specific day in a specific lab, where instruments recorded a brief, controlled burst of star-like fire that gave back more fusion energy than it took in. It was the instant when a page in a physics textbook quietly became part of your real-world options. The next time your lights flicker, or a summer heat wave pushes your grid to the edge, or a notification warns that a data center has gone down, you will feel that old, uneasy dependence on the big, fragile system holding your life together. When that happens, remember that deep under concrete, inside a lab full of lasers and detectors, a group of people already proved that your species can light a tiny star and hold it briefly in human hands. One evening soon, when your city goes dark for real, the real question will not be, can you make a miniature star? It will be, what did you choose to do with the moment when you first learned that you could? If you liked this video, do like and subscribe to this channel. Comment below on which scientist would you like to watch next.